Hello everyone. So, you probably thought that you were officially done after I announced in the last video that it was going to be the last video ever, but I just decided I couldn't quit angular momentum soon enough, so we're going to do one more. So, this last video is related to the practice problem sheet I posted on there. And you'll notice I'm looking at kind of the answer key right now for it. So this isn't quite the same thing, but in case you're kind of curious what it is, you are going to where it says angular momentum example problem on Canvas, clicking that, because we're going to practice just doing some more angular momentum and kind of going through that. So this question is focused specifically on what happens when you have something that's moving in a straight line that doesn't seem to be rotating, that actually causes something to start rotating once it runs into something else. All right, and I know that was a lot of words said at once. Basically, what happens if I shoot something and instead of it causing the object to move forward, it causes it to spin? So, in this case, this particular question is focused on the fact that I have two, I believe they're steel spheres, on the edge of a massless rod. And in the middle is a rotation point. So they're designed so that they can just basically spin around and around and around. Now, right now, they're not spinning at all. And what I do is I actually launch a clay sphere at one of them so that the clay sphere sticks to this. All right. Now, of course, you can just kind of imagine what's going to happen. As soon as I hit this and it sticks, it's going to cause this system to start to spin. Now, why this is rather interesting is because, in theory, you would think that this sphere, the clay part, does not have any angular momentum. But in fact, it does have angular momentum because it has to in order to follow the rules that angular momentum has to be conserved. All right, because remember, it doesn't just magically gain angular momentum. So, to do this, what I'm going to do is I'm going to talk through the first four. So I'm going to do it on my key that I already have. But then you are going to do part 5, and you're going to see if you can prove what's already been discussed. All right, and you'll understand that as we get to part 5. So right now, we're going at the first 4 parts. Okay. So, I've drawn on my little diagram right here that the axis of rotation is right at this particular point. Now, this object that is coming towards the system we want to rotate, we can kind of refer to it as a point mass. Okay? And we have a very specific formula for angular momentum for things that are point masses. And what they are is basically, we say the angular momentum of that object is the mass of the object times its linear velocity times this r usually represents the distance away from the axis of rotation. So, in this case, even though this object looks like it's going in a straight line, when it reaches the metal sphere, for a split second, it can't tell, and the axis of rotation can't really tell, if this object wants to keep going straight, or if it's just going in a circle and it happens to be going at the very position right here that it would be moving if it was going in a circle. So what we do is we say this thing must have angular momentum. Now, the angular momentum of this object is going to be dependent on its mass, how fast it's moving, and how far away from the axis of rotation it is. So you'll notice I've already kind of gone through there and filled out some of that stuff. The mass is just m. The velocity it's moving at is just some v naught, some constant velocity. And the distance from the axis of rotation is going to be the length of the rod divided by 2, because it's half the distance of the rod. So the angular momentum of the system at the moment that this object strikes the metal sphere is going to be equal to the mass of that clay sphere times its velocity times the length of the rod divided by 2. All right, and that's slightly different than the original formula we used for angular momentum, which was this one right here, that it's equal to the moment of inertia times the spinning velocity. So what we're going to see is that angular momentum can happen even if something looks like it's not originally going in a circle or going kind of rotating, based off of if it causes something to rotate. Now that leads nicely into the next question. What is the angular momentum of the system after the collision? Well, right away, before and after the collision, whenever you hear that, it doesn't matter if it's linear momentum, angular momentum, you should immediately think to yourself, oh, they've got to be the same because momentum is conserved. And this is no different here. So the angular momentum after the collision is the same as it is right before the collision. So it's still going to be equal to just the mass times the velocity of whatever that original clay sphere was times the length of the rod divided by 2. All right. Now, this is where we want to do some calculations. I want to calculate how fast, what is the angular velocity of the system after the collision. All right. Now, at this point, now the system is rotating. So I'm going to go back to using my original formula for angular momentum for objects that are rotating, which is going to be equal to the moment of inertia times the angular velocity. Now we're looking for this angular velocity, so that's what we're going to end up finding. So if you want to underline that, just that you know, that's what you're looking for. We know, we have some answer for angular momentum, so we can put that in for L. But what we're left with is we don't know what the moment of inertia is. And unfortunately, it doesn't really say explicitly what this is. And this is actually a case of something where you have an object that has kind of a weird setup. And what I mean by that is that whenever you have a point mass, or you have something that's not kind of a uniform shape, in this case, you have each metal sphere on the end, and then the other little clay sphere. What you're going to have to do is, in order to figure out the moment of inertia of this system, all you do is you take the moment of inertia of each object and add it together. Now you're measuring the moment of inertia of the object with respect to the turning point. So you'll notice right here, I have it kind of written out. So we start, let's go just from left to right. We start with the leftmost object. Now the moment of inertia of a point mass going around some turning point is just equal to the mass of the object times its radius squared. Basically the radius of the circle it's making. All right. Now on the other side, we can basically assume that we have two of these point masses. So it would be, the way I've done it is basically I just did 2 times the mass times the radius squared because they're both point masses. All right. So you're left with basically that the moment of inertia of this whole system, these 3 point masses added together, is 3 times the mass of one of them, or just times the mass of it, times the distance away from the axis of rotation. And because they all have the same mass and they're all the same distance away, it kind of makes it a little more uniform. All right. Now, when we do that, you'll notice over to the right side, I've done a little calculation. What we do is we just replace the big M with the little m, just to represent the mass. We replace the r, that radius, with the distance from the turning point. In this case, it's L divided by 2 because it's half the length of the rod. So when we go through and do that, we actually get that the full moment of inertia of this whole system is just equal to 3m times the length of the rod squared divided by 4. All right. So now we're in business because we have something that we can plug into for the moment of inertia. And you notice right here, I still have the same thing. I have the original angular momentum equals now the moment of inertia times the angular velocity. If you solve for the angular velocity, you'll get that the angular velocity, how fast this thing is spinning, is just equal to 2/3 times the original linear velocity of the clay sphere divided by the length of the rod. Okay? And what that means, looking at it, is that first off, it doesn't really mean a ton to us because you're like, why? Who cares? There's linear velocity, there's length of the rod. Let's think about it physics-wise. If I make this rod longer, so the length gets bigger, you'll notice the velocity actually, the spinning velocity goes down. It doesn't spin as quickly. And so also, if we think about it, it makes sense. If I make this velocity larger, if I give it more velocity when it runs into this, it actually spins faster, which honestly, that makes sense. If I shoot something really, really fast and it runs into this and gets stuck, it's going to cause it to spin really quickly. So we're just looking at this relationship and trying to think about physics-wise, conceptually, if that makes sense. And at least for my eyes, I think it does. Now, the fourth question. Imagine the masses all move to the center. So what I mean by that is that imagine that these two masses, the two metal spheres, will move to the center. All right, so they're right at the turning point. How's this going to affect the angular velocity? Now, what this does is that we have to think of the fact that the moment of inertia is going to be smaller. Because of that, if the moment of inertia is smaller, that means by the law of conservation of angular momentum, in order to balance it out, the system has to actually spin faster. So if I launch this at this system, and I have these two objects in the center as opposed to being on the edges, the angular velocity that we calculate should be faster than it is originally. Now, what's interesting is that the angular momentum of the system is still the same because this object has the same mass and velocity and distance from the turning point that it did before. But it affects this particular part because the moment of inertia is now different. And that, ladies and gentlemen, is what you are about to calculate. So for part 5, the last piece of this is I want you to prove that what we said in part 4 is correct. So I want you to kind of pause the video. I want you to prove that the angular velocity of this setup is going to be greater than it was originally by literally solving for the angular velocity. All right? Now, the one hint I'll give you before I let you go to do it is that you need to think about how far away are these two spheres. If I move them to the middle, how far away are they from the turning point or the axis of rotation? And what I'll tell you is that they can be a distance of 0. They can be right there. They are going to be on top of the rotation point. So it's not a problem to say r is actually equal to 0. All right? So that being said, ladies and gentlemen, I want you to pause the video, and I want you to solve for the angular velocity. Once you think you've got it, come back, and we'll wrap it up. All right? So hopefully you had a chance to kind of work through, ladies and gentlemen, and answer question number 5. I'm just going to do it on this little PDF because I'm not really worried too much about answering it. So if we go through and we make the change that now there's just these objects are now here, all right, and this one still hits it. What we do is that now with the new moment of inertia, remember you're just adding all the, you can, when you do moment of inertia with point masses, you just add them up one at a time. Well, the first object, the first metal sphere, is now a distance of 0 away. So actually the first moment of inertia is 0, doesn't have one. The same thing is true for the second metal sphere. It's also at a position of 0, so its distance from the turning point is 0, so actually there's no moment of inertia there either. Which means all we're left with is the moment of inertia of the final one, which in this case is going to be just mr squared. It's the formula we use. Okay. And then what we do is that we know it's just the mass m, so we put in L over 2. So we're left with now, we have that the original angular momentum, m v naught L over 2, is going to be equal to this, which is going to be m L over 2 squared times the new angular velocity that we don't know yet. Now, of course, you can simplify some stuff out. You can get rid of this mass. You can actually get rid of an L. Since this is L divided by 2 squared, you can actually get rid of an L over 2 on this side and the L over 2 on this side. So you're left with basically V naught equals L over 2, and I apologize for this really good handwriting, times the new spinning velocity. Once you move all that around, you should get that the new angular velocity, just kind of looking at it, is going to be equal to, so the new omega is just equal to 2 V naught over L, which right away is definitely larger than the one we got previously, which is 2/3 V naught over L. So even though we did a little math work and it seems kind of like, why do we just focus on the algebra? What matters here is that we just proved conceptually what we discussed in part 4. And what we proved is that the spinning velocity is going to be significantly greater if you cause the moment of inertia to be smaller of this system. All right. So it's just a kind of a situation and discussion about how you can adjust how fast something spins and why it matters where you put something in a rotating system in terms of affecting the angular momentum and maybe affecting the angular velocity. All right. So with that being said, ladies and gentlemen, that's just kind of one practice problem to go through and discuss angular momentum. There will be a web assignment that you can go through and practice, but from this point on, the rest of the stuff you're going to see is going to be review stuff to prepare for the AP exam. All right. So with that being said, ladies and gentlemen, have a great rest of the day, and I'll talk to you later.